All right, so we are going back to looking at how bond angles and bond lengths are impacted by various things. So with inorganic chemistry and all of chemistry, but chemistry, you will find that there are just a handful of things that have a big influence on predicting shapes, structures, reactivity, those kinds of things. And electronegativity is probably first and foremost among that. We have sterics, or size, and we have, we'll talk about hydrogen bonding, that influences it.
You said it affects size and shape.
It affects a whole bunch of things. So it affects the bond angles, the bond lengths, the reactivity, and all
This is
kinds of
electronegativity does all of this?
these things.
Affect
So
the
these
bond
are influencers
of bond length.
of a lot of things. They influence bond length, they influence bond angle, they influence polarity, they influence electronegativity, or not reactivity. So when you're asked why is such and such happening, these are often the answers to why. We talk a little bit about relativistic effects. What's in there? And that's the really heavy elements have the electron moving really fast, and so they actually weigh more. And then we have polarizability. We'll get to that one later. So we're mostly focusing on electronegativity and sterics, and we'll get a little bit of the hydrogen bonding if I can get this PowerPoint to pull up. Just open that guy. Okay. All right, so we had talked a little bit about reminders from freshman year with VSEPR theory. And so this is using the trigonal bipyramidal class as an example. But this is showing that when you have a lone pair, that's going to push on the bonds more than the bonds are going to push on each other. So if you look at that central figure there, you can see the fluorines are kind of pushed away from that lone pair. And we've also seen this, we talked about ammonia and water have smaller bond angles than the ideal, but double bonds will also do the same thing. And so if you look at the left-hand side where we have two lone pairs, those two lone pairs have the pushy power of the the two double bonds have the pushy power of the one lone pair. So it kind of straightens it out. And so you can see on the far right-hand side where we have the lone pair on one side and the double bond on the other side, they just about balance each other out. So double bonds and lone pairs can kind of push things away from one another. Let's see. So this is also showing that same idea that if we have the lone pair like we do on the one in the middle, our bond angle gets smaller, or if we have a double bond, that bond angle gets smaller. All right, so that's stuff we covered freshman year. These were electronegativities. And then we started looking at this chart that was looking at the bond angles. So these are all in the tetrahedral class. So they have 3 atoms and 1 lone pair on the central atom. And so what's the ideal bond angle for the tetrahedral class? 109.5. So if I'm looking at methane, I would expect it to be 109.5. And in ammonia, it's right around 107. So it's just a couple of degrees smaller. And you can see in these cases that that's not what's going on. We have it even underneath 100 in a couple of places. And then we have this trend going on for how that bond angle changes depending on what is attached to it. Now, this table is in your book, so you have a reference to that. And it's also here on this slide. So one of the things that we talked about was size makes a difference. So the fluorine is smaller than the chlorine, which is smaller than the bromine. So it's just possible for them to get closer together, whereas the bromine is so big, it's going to push out that that angle. So we expect the smaller outside atom to make for a smaller bond angle. But there's another explanation the book goes into, and we kind of need this explanation for some of the other things that we're going to look at. And so what this is that when we have a more electronegative halogen, so fluorine's the most electronegative, that our bond doesn't have the electrons shared like a nice straight stick from one end of the bond to the other, but rather the electrons are spending more time near the fluorine. And then when we have the bromine, we kind of have the other situation going on. Phosphorus is a little bit more electronegative. So if we think about our bond, let's do the phosphorus one. The two bonds are going to be closest together near the central atom, the phosphorus or the sulfur. So this end is where that makes a difference. So if I've got a bond where the electron density is pulled towards the other atom, then the part close to the phosphorus is not pushing away as much. But if I have the bond where the electron density is closer to the phosphorus, as is the case in the phosphorus tribromide, because phosphorus is more electronegative, these are going to push each other away from each other because the two bonds have the electron density very close to the phosphorus where the bonds are close to each other. Out here, the bonds are far from each other anyway, so it doesn't matter. All right, does that kind of make sense?
Can you say that one more time?
Okay. So these lobes that I'm drawing are kind of where the electron density is. And so the fatter part is where there's more negative charge. So when the negative charge is far from the phosphorus, then the bonds can get closer together because it's at the phosphorus where the bonds are close together anyway. But when that negative charge is at the phosphorus end, since that's where those bonds are really close together, they repel each other a little bit more. So these two explanations kind of go hand in hand. But we'll see that this explanation is going to help us a little bit with the next thing that we look at. So we just started looking at the example where we're changing the central atom. On the central atom, again, we have to be thinking about those bonds being closer together. We have sort of an odd thing going on, and you may have noticed this with the phosphorus, that those bond angles had gotten smaller than 100 degrees. We were really deviating quite a bit from that 109.5 ideal angle. Well, we're noticing the same thing here. For water and nitrogen trichloride, we're still within a few degrees of that 109. But when we change the central atom to the next row down, we go way down. And then next row down, we go even further down into a smaller angle. So we get smaller and smaller angles as we go down. So if we think about what this might look like pictorially, what we're saying, and so notice that we have the outside atoms are the same in each column. So in the first column, they're all hydrogen as our outside atoms. We have a scenario where we have our typical water molecule, and this angle is our 104.5. I should probably draw those a little farther apart. Hard to see. And then when I make my central atom bigger, instead of still having this where we would we kind of expect that to be the same angle, it actually gets closer together. So this is a little counterintuitive. Why would making the central atom bigger cause the bond angle to get smaller? Why would those atoms get closer together? Okay. So there are several explanations that we have for this. And, you know, we don't have the God handbook that gives them to us. So as scientists, we're just trying to see what is the explanation that fits the most scenarios, that is most consistent. So one of the explanations is going back to this electronegativity. So part of it is that the more electronegative central atom, oxygen versus sulfur or selenium, is going to draw that electron density closer. Okay, so here I have the oxygen really drawing in that electron density. And with the electron density close to the oxygen, it's going to push the bonds out. In contrast with my selenium, the electron density is further out. I think selenium has a lower electronegativity than hydrogen. I'm not positive of that. But in any case, these two bonds do not repel each other nearly as much. Okay, so we can use that same explanation for both of those. That one's a little bit harder to grasp than these other two, but the other two, especially the second one, isn't going to give a very satisfactory explanation. It's just going to say, this is what we observed. Okay. So our second explanation is ligand close packing. Ligand close packing says that for any central atom, a given external atom will like to be a particular distance away from other external atoms of the same kind. So in this scenario, what we're looking at is the boron in the middle and the fluorines on the outside. So we have lots of different examples with a third ligand that is something else, just showing us the consistency here. And so what we see is that the bond angle changes a little bit, but the fluorine distance is pretty consistent. Okay, it's about 226, 227 most of the way through there. And then if we change this from a tetrahedral class to, well, I guess they're both tetrahedral classes, but if we change it from a trigonopyramidal that has a lone pair to a tetrahedral, no, it doesn't have a bond.
Trigonal planar has an infield.
Yeah, because it doesn't, it's electron deficient. Yeah. Without the drawing of the dot structure, I forgot that. Yeah. So we're going from trigonal planar to tetrahedral. Our bond angles changed, right? So we went from 120 for the trigonal planar to about 109 for the tetrahedral, but our fluorine distance still is right in that same area. Okay, so ligand close packing is saying that our two ligands want to be a certain distance from each other. So they're just going to slide around the outside of that central atom until they just bump into each other. And whatever bond angle gets created from that, that's the bond angle you end up. All right. Then our third explanation is the p orbital takeover. So you talked about valence bond theory freshman year, and you used it quite a bit in organic chemistry, and it works really well for organic chemistry, and it does not work at all for inorganic chemistry. So on the left-hand side here, you can see that this works really well if our central atom is in the second row, carbon, nitrogen, oxygen. Golly, those are elements we use all the time in organic chemistry. Of course, we're going to use this model. But once the elements get bigger, it doesn't really work very well. So what we say is that the p orbitals are not mixing much with the s orbitals. We don't really have hybridization going on. Really, we have independent p orbitals and independent s orbitals, and then they contribute to a molecular orbit. And we'll get into molecular orbital theory in a chapter or two. So since we have the bonding with the p orbitals sit on those coordinate axes, the x, y, and z axes. So they're all 90 degrees from each other. So when you're finished jotting this stuff down, we'll go back and look at that data, and we're going to see that the bond angles that we have were very close to 90 degrees. Oops. Oops, too bad. Okay, here we go. With the selenium and the sulfur, we had 92 and 90. With phosphorus in the middle, it was 100, but we've got chlorine as an outside atom. So it's bigger than the hydrogen, so it's taking up a little bit of space. And then arsenic is even smaller than that. So we've got our ligand atoms wanting to attach to an individual orbital rather than some theoretical hybrid orbital. And so this is a chart where we can kind of look at a lot of these different trends and see how those things follow along. We can look at changing the central atom. We can look at changing the outside atom. We can compare first row to second row and those kinds of things. But what you'll notice is for our bond angles here for our third row and heavier, they're very near 90 degrees here, very near 90 degrees here. And when they're not near 90 degrees, when they're closer to 100 degrees, it's when we've got a larger atom like chlorine or bromine that is forcing that angle one. Okay? So 3 explanations for why our ligand atoms form a smaller bond angle when we have a heavier central atom. All right, so that was mostly electronegativity. Sterics also plays a size. And so they go in your book, they go into more detail in these trigonal bipyramidal ones because you can kind of look at it from a couple of different angles. Allows you to play with it more. So we're going to pay attention to bond lengths both on the equator. Remember, we talked about equatorial attachments and the axial attachments. And so you'll notice that for the phosphorus to the fluorine on the axial attachment, it's right about 160, just shy of 160. And that doesn't change a whole lot no matter how many fluorines we have. But if we look at the fluorine that is attached equatorially, when it is, oh, that one is the one that doesn't change much. I'm sorry. The fluorine that's attached equatorially doesn't change too much when the chlorine is very far away from it. So the equatorial position is 120 degrees away from it. And so that didn't affect it too much when we added 2 fluorines versus 1 fluorine. but for the axial position, it did push it just a slight bit longer. So the size does have an impact. So the point of this is that sometimes other ligand atoms can create barriers to an ideal bond length. So the fluorine probably wants to be a little closer to the phosphorus than the 158, since we can see that it can be 154, but the presence of the chlorine is pushing it a little farther away.
And that's just because chlorine is bigger.
And it's just because it's big. We can also see this when we have ligands that are groups rather than individual atoms. So if we started replacing this with a methyl group, a CH3, or when we get into transition metals, some of our anions are going to form ligands. And so like the nitrite ion is one of the ligands, and that's 3 atoms. Oxalate as an ion becomes a ligand. Ethylene diamine. So we have bigger things. And so the bigger it is, the more that influences how attachments are made, sometimes whether or not attachments can be made at all, but also the lengths and the bond angles and the electronegativity or polarity. Okay, so this is another example. We've talked about ammonia a couple of times. So ammonia's bond angle is about 107. We predict that to be a little less than the 109 because we've got that lone pair that's pushing on it. And then on the other side, and I didn't label it, but it should be nitrogen triiodide. So we replaced all the hydrogens with iodine. So purple because iodine as a solid is a dark purple color. So that bond angle, it's kind of hard to find the bond angle for it because this is a very explosive molecule. It's what we call a contact explosive, meaning like you don't have to apply heat or electricity, just touching it can cause it to go off. And so part of this is because the iodines are so big that they are forcing each other away from that nitrogen. That if I took 3 iodines and set them down, that I really have a lot of room for that nitrogen to be in the middle. The iodines really don't want to be as close to each other as they are. And so you'll notice the bond angle is actually greater than our ideal. Even though there's a lone pair, that bond angle went out to 111, and that's an approximate, but it's larger than 109 because of the strain due to the size of the iodine. And I couldn't find data on the bond length, but the nitrogen iodine bond length is also quite a bit longer than it would be if I had 2 hydrogens in 1 ion. Okay, which means longer bonds. What does that do to the strength of the bond? Longer is weaker. So this becomes a very weak molecule, easily falls apart and allows the atoms to rearrange themselves into much more stable molecules, including ammonia. Provided there's like hydrogen nearby. All right, so this is looking at a couple of different things. First of all, the CH3 is a bigger group, right? So thinking about its size, but it is also a lot less electronegative than fluorine. I think it is slightly electron donating. Is that what you say in organic chemistry? I mean, it'll be a little bit different with phosphorus compared to carbon anyway.
Yeah.
Okay, so your fluorine's clearly the more electronegative one. The methyl group is less electronegative. And as we add more of those less electronegative groups, but also those bigger groups, notice what happens to that axial bond length. We go from 161 to 164 to 168. So the size of that outside molecule makes a difference, right? But we can also go back to that story about where the electrons are in the bond. Because if the methyl group is not wanting the electrons, if it's donating the electrons, those electrons are close to the phosphorus, and we're back at this scenario.
Methyl groups usually don't have much effect. Some carbon groups are, I guess, tend to be more kind of electron.
Well, remember, we're
withdrawing.
comparing it to fluorine. So fluorine is the extreme of having the electron density out here. So methyl group does not pull that electron density away. More of it is closer to the phosphorus. Okay. So, so in this case, that is telling us that the methyl groups are putting that electron density close to the phosphorus. Well, they can't really spread out any further than that 120-degree angle, but that can influence the other two attachments, the axial attachments, kind of pushing them further away. So we've got several things in play at the same time. All right. So this looks like it might be a similar story, but notice that this isn't a methyl group. Right? This is a carbon trifluoride, or I don't know, kind of like chloroform or fluoroform, but there's no hydrogen.
And that would probably be electron withdrawal.
It is. And so that group is similar to in electronegativity to the fluorine. So what this allows us to do is see, is this an electronegativity thing, or is this a size thing? And when I only have one of the CF3 groups, then the two arrangements with it either on the equatorial region or axial, those are interchangeable. So notice the equilibrium arrows here. Either one can happen. And they constantly interconvert. So it's not like one of those things where you get like a racemic mixture, right-handed and a left-handed, but if it's right-handed, it stays right-handed, and it's left-handed, it stays left-handed. In this case, the molecules will interconvert, provided they have the proper phase that they can do that. But once I start adding more of them, the larger groups want to stay farther away from each other. So they can get farthest away from each other by being axial if there's two of them. But if there's three of them, then I'm back to the story of creating that 2 90-degree angles. I don't want to have 90-degree angles with those big old groups. So I put them on the equator to spread. All right. So the long and the short of it is we can explain the arrangements of molecules, both with electronegativity, thinking about where in the bond the electrons are, and with size or sterics, how big the molecules or the atoms are. And I think this is my last slide. I'm not sure what's.
Oh, and the last two on the side, like, there's not much difference between them, right? Because of the volumes.
It's just the different positions.
Okay.
Yeah, so because the CF3 group is bigger than the fluorine group, if there's just two of them, they're going to get farther away from each other. But if there's three of them, then they're going to go on the equatorial position, so they can still be far away from each other and not have that 90-degree angle between the two of them. So usually when we talk about polarity, we talk about polar bonds and how much the electronegativity of the given elements affects the polarity of those bonds. So if we have like a hydrogen fluorine bond, we know that fluorine is more electronegative. It's more electronegative than pretty much everything. So we would draw a dipole arrow that looks like this to indicate that it's polarity. And then if we think of something like ammonia, oops, ammonia has a nitrogen in the middle. The nitrogen is more electronegative than the hydrogens. And so we have a polarity that looks like that. So are we all comfortable with that? Seen that before? Doesn't seem too weird. All right, so one thing that we kind of gloss over in beginning chemistry is that lone pairs actually have electronegativity too. And so in this case, I'm gonna put another color in here. The hydrogens don't want the electrons as much as the nitrogen does. So the bonds are polar towards the nitrogen, and the nitrogen is not as electronegative as the lone pair, because lone pair doesn't have a nucleus. And so this ends up being, both of those are synergistic. They complement one another. They all drive the electronegativity in the same direction. So for ammonia, the net dipole is 1.47. And I want to say the D stands for divide. And I have a similar story with oxygen. Where the oxygen is more electronegative than the hydrogen, but the lone pairs are pulling in that same direction. This one is 1.85 divide. The question is, what happens when I reverse the polarity of the bond? So now the fluorine is more electronegative than the nitrogen, drawing the electron density away from the nitrogen, right? But the lone pair is still drawing the electron density away from the nitrogen as well. So would we expect this to be more polar or less polar than ammonia?
Less polar.
Less polar. And in fact, its dipole moment is about 0.23 divide. So even though we have the fluorines there, and we usually think of fluorine as making things more polar, this makes it less
I
polar.
guess the question is like which direction the overall dipole moment would be in.
Let me check.
Because you have 3 fluorines, you also have a lone pair. Of course, the fluorines also have lone pairs on them
It is
too.
actually towards the fluorine in this direction. So I guess fluorine is a little more electronegative than the lone pairs, probably because the fluorine also has lone pairs.
It has like, you have like 9 lone pairs down there
Yeah,
versus 1.
so there you go. All right, so next thing I want to look at is hydrogen bonding. That was hard to see. And I'm going to put bonding in quotes because is this a covalent bond? Not really.
It's an anaerobic molecular force.
Right. So when we think of covalent bonding, that's intramolecular, it's happening inside of the molecule. The intermolecular forces are happening from one molecule to the next. And so ions tend to be sort of an in-between thing. They're not really a bond either because they're not really sharing anything at all. So they're not inside, but at the same time, when we think of a crystal, like they're inside the crystal, so they're on the border. So covalent is strongest, then ion-ion, hydrogen bonding fits in next. What are the others?
The Vander. Yeah,
I know what you're thinking of, van der Waals. That's not quite right.
because there was the London version.
That's
that
it.
was the last one. But there was one that was above it. That started with a
Well, like a dipole.
Dipole. Okay, so usually we do not include van der Waals in this set because these are attractive forces. Van der Waals is the idea that when I have two atoms next to each other, the parts of the atoms that are next to each other are the electrons. So they're going to repel each other a little bit because of that. So if they're not bonding, then they repel each other from getting too close. But if I have a dipole, it's also going to bring it in. So it's kind of a counter example. So remember on senior orals, you're going to need to know the order of these, and we might give you some molecules like, say, the water over there. So which of these does water fit into? Hydrogen bond. And if I had methane, that's going to be London dispersion, right?
Question. What about like ion dipole?
Yeah, so those kind of fit in between. That would be if you have a mixture. So if I have a pure substance, I just have these.
Yeah.
But if I have a mixture of things, or if I have certain biological molecules like a fatty acid anion. So we could have in here ion dipole.
Yeah.
And there's not really an ion hydrogen bonding because hydrogen bonding doesn't hydrogen bond with ions. It hydrogen bonds with very specific atoms.
What about like metallic bonding? Is that?
It
Or
follows kind of a wide range. Okay. What if I had a dipole and I had dispersion forces?
dipole stronger?
Dipoles are stronger. We call this dipole induced dipole. And that's true whether it's a dipole or hydrogen bonding, because as a general rule, if it's got hydrogen bonding, it's probably polar. And then I could have this extreme would be ion induced dipole. And it's really hard to rank which is stronger because that's going to depend on how strong of an ion you have, how fluffy of a molecule you have, those kinds of things. But do keep in mind as you prepare for senior orals this year, or as you are marking your notes of things to prepare for next year, that this is something that does show up on senior orals. Okay, so back to hydrogen bonding. We said it only does very specific atoms. So we say the hydrogen is attached to a very electronegative small element. Which basically boils us down to three elements. What are those?
Nitrogen, oxygen, fluorine. Nitrogen.
All right, now if we think about hydrogen and fluorine, they each can only form one bond. So really that's the only molecule, HF, that can be hydrogen bonding just by itself. But we have lots of combinations of these, and that's going to include water and ammonia, but it's also going to include amines, right? And it's going to include alcohols, and it's going to include carboxylic acids. So this is going to have some internal hydrogen bonding. Sometimes when we have mixtures, we can also get hydrogen bonding to something that doesn't have a hydrogen. So let's say I had formaldehyde and I also had water. This hydrogen is still going to be attracted to the lone pair on that oxygen, even though this oxygen doesn't have any hydrogen. Okay, So sometimes you can have hydrogen bonding to things that technically by themselves don't have hydrogen bonding. Molecules with lots of alcohol groups on them include sugars. And that includes some of your DNA stuff, the nucleic acid sugar thing. I forget what they're called. You guys have had biochemistry. But just be aware that if you're doing a biochemistry question, hydrogen bonding is a part, okay? And then very important molecule to know how to make or to draw is an amino acid. You got the name amino, so amine on one side, acid, and the acid group on the other side. And then we got a hydrogen and something else. Anytime you have an amino acid, you've got the potential for hydrogen bonding. And that plays a big role in how those proteins kind of wind around and form each other. That's why you end up with things like the alpha helices. You get the hydrogen bonding cooperating. Okay, so it does show up. It's stronger than a dipole-dipole. It makes a difference in things like melting point and boiling point. So the way that we study intermolecular forces as freshmen or in general chemistry, we pair that with some of those properties that show up again and again. So if I'm looking at I'm going to list some things over there. Hydrogen bonding is going to cause several of these things. If I'm looking at melting point, boiling point, vapor pressure, surface tension, causes all of those properties to be greater than expected for the size of the molecule. So one example, if you go back on my old exams and quizzes, I often ask a question like this. They have a table in your book that shows, what is this? The boiling point of several different chemicals. And if I look at water, what's the boiling point? 100 degrees Celsius. Now, typically, we would expect the larger the molecule, the higher the boiling point would be, because there's more electrons, because it's heavier, so they tend to be more attracted to one.
Sulfide gas.
Yes, hydrogen sulfide is a gas at room temperature. Its boiling point is about, looks like -60. I'm guessing from this chart. I don't have the actual numbers. If I look at hydrogen selenide, this one looks closer to -50. And hydrogen telluride looks closer to 0. It's just shy of 0. So these, as I get heavier, the boiling point goes up. But this is the opposite trend. So the graph looks like this. Well, so I'll often say that of these four, hydrogen sulfide has the lowest boiling point. I could use melting point. Explain why, or I might just give you the four and ask you which has the lowest. And so this is where you have to remember that the hydrogen bonding is gonna make this really small molecule behave like something a lot heavier. So even though hydrogen telluride is a lot heavier than water is, the boiling point for water is much, much higher.
Some compounds with selenium and mercury.
All I know is they're stinky, just like hydrogen sulfide.
That's probably why we don't know much of that.
Yeah. All right, so, any questions? We've mostly covered chapter 3. If in looking at chapter 3, you have questions over things, let me know and I'll try and get that homework assignment posted before class on Wednesday, so that I can kind of talk to you about what you'll need to know, what to expect. All right,